Hello, my name is Estella.
And my name is Christina.
And today we're going to explore acids and bases using black beans. So first we're going to put it into a heat-proof container, and then we're going to add boiling hot water to it so that we can extract some of its color. And this will then steep for about 30 to 60 minutes. So now after an hour in hot water, the black bean soaking water is a dark blue-purple color, and we're going to use this and the properties of the molecules that are in this water to determine how acidic or basic a solution is. To begin with, let's make sure we all know how to characterize acids and bases. Acids are solutions that contain a majority of H+ ions, or protons, and are able to donate them to other substances. Bases, on the other hand, have a majority of OH- ions, or hydroxides, and accept protons. Together, protons and hydroxides neutralize each other and form water. Acids and bases are commonly found all around us in our daily lives, from food and drinks to cleaning agents. For instance, acidic foods are typically sour tasting, whereas basic substances are bitter tasting.
Biological molecules are especially sensitive to the amount or concentration of acids and bases in the environment. Something too acidic or basic will lead to an irreversible damage. Fish and plants, for example, will not tolerate excessive protons and hydroxides in the water. Indeed, people have gotten chemical burns from strong acids and bases like battery acid or lye, respectively. One way to measure the concentration of protons is by pH, which is on the logarithmic scale. pH ranges from 0, acidic, to 14, basic. Indicators like black bean juice changes color depending on the proton concentration. This happens because the H+ ions will protonate the color molecules in a concentration-dependent way.
So let's find out what the color range of the black bean indicator is and how that corresponds to the pH scale. First off, let's put on some gloves, because safety first. We'll first put in an equal amount of black bean juice to each of these clear containers, which will let us see the color changes the easiest. Okay, so let's now add the most acidic solution, which has a 1 molar proton concentration, to our indicator. Let's do some mixing, and it's changed into a vibrant red color. Next, we'll add 0.1 molar proton solution to our indicator. This has 10-fold fewer protons than the previous solution. And then after some mixing, looks like it's turned a pale pink.
Now let's do the same thing with bases. I'm going to start with a weaker base of 0.1 molar hydroxide solution and add that to the black bean juice. After swirling some, it has turned a dark blue-green. And to finish it off, the stronger base of 1 molar hydroxide, after mixing with the indicator, turns the bean juice a yellow-green.
The colors here can be corresponded to the actual pH values that we can measure. This can be done by many methods, including a pH meter or by these commercial test strips. These strips are really useful for maintaining the pH of fish and soil, for example. The strips in particular have 4 different indicators that are sensitive to different pH ranges. So to use them, we simply expose the strips to a solution, or a fish tank, and match it to the color pattern on the box to determine the pH. And it looks like the water in this aquarium has a pH of about 6 to 7, which is ideal for these little guys. Alright, so let's use these strips to measure the solutions from our experiment. So I'm going to add some solution on top of these strips and wait for the color to change. And for the 1 molar acid, it looks like it reads at a pH of 0. We can similarly measure the pH of the 1 molar hydroxide solution. So we add some solution on top of the strip, and it has a pH of 14.
So, I'm wondering, what would happen when we combined an equal amount of proton and hydroxide ions together? What would the pH be? What would the color be? We're going to start again with the black bean juice, getting it all distributed. As we add some of the 1 molar base and then some of the 1 molar acid, the colors are swirling and bouncing between the green, yellow, and red colors. Until finally, when we have an equal amount of both acid and base, what's happening? That's right, it's turning into the color of the black bean juice. It's neutral, that is, a pH of 7.
Now that we have a pH color range, let's use the scale to approximate the pH of common household goods and foods. So here I have some bleach, and some baking soda,
some coffee, and lemon juice.
I'll first add some water to the baking soda so that I can dissolve it into a solution, and that solution can then react with the black bean juice. So I'll mix this until it's mostly dissolved and fairly clear. And then I'll add the juice and mix it until it's uniform in color. So what color is this? Let's see. It's not particularly pink or acidic. It seems to be just a bit past neutral, so a very weak base.
Let's measure the pH of coffee next. I'm going to add some black bean juice to the coffee. It's pretty dark, so I can't see any color change. Looks like the scale only works with very lightly colored solutions, otherwise the color won't be accurate.
Next up, I have a small amount of bleach here. Bleach will, for lack of a better word, bleach your clothes, but it can also irritate your skin and eyes. So if you're planning on testing this or any other cleaning agents at home, please do so with adult supervision. Alright, I've just added some indicator. What do you think? That's right, it's a strong base.
And now we have the lemon juice. What do you think the pH of this is going to be? Well, let's find out. So I'm going to add again the black bean juice pH indicator. Oh, and it's turning immediately. It doesn't really appear to be matching the basic scale, but look, it looks very acidic.
As one last test case, I want to measure the pH of liquid dish soap. Since dish soap is quite viscous, I have to dilute it with water first. Then once I have a soapy solution, I'll add in our indicator juice like before. It's changed to a dark blue color. So definitely not as basic as the bleach we just tested, but it does appear to be a weak base and kind of similar to the baking soda that we had measured earlier. So that is the last measurement we're doing for this demo, but we encourage you to try this experiment at home and measure the pHs of some of your favorite household items. Maybe you have some interesting solutions that we didn't get around to testing.
As scientists, being able to accurately measure pH is particularly important since pH influences chemical reactions in the result of our research. So, as budding scientists yourself, hopefully these experiments give you a sense and appreciation of how acids and bases are present all around you in your daily lives.